Right, in this video I'm talking about equilibrium. It comes directly from moments of a force. Remember, we said that a moment of a force is the turning effect of a force, and it's given by the product of the force and the perpendicular distance, the line of action of the force from the pivot. And we talked about clockwise and anti-clockwise moments. And we said when a body is balanced, we have the clockwise moments equaling the anti-clockwise moments. Now this leads us to equilibrium. A body is in equilibrium or in balance when it has no tendency to turn or to move. There are two conditions for equilibrium, and then these are, first of all, the sum of the clockwise moments should equal the sum of the anti-clockwise moments about any point. So when you take the clockwise moments about a point, take anti-clockwise moments about the same point, you should get the same value for it, the equilibrium to be there. Then the second condition, the resultant force in any direction is zero, which means the sum of forces in one direction should balance or equal the sum of forces in the opposite direction. Now to verify this equilibrium, you need a spring balance. You need a piece of string to hang the spring balance. You need a uniform meter whose weight acts at the center. Remember, uniform means weight acts at the center. Then you've got weights on the either side of the halfway mark of the meter. As you add weights, you restore the balance. You find that the forces from the weights and the weight of the meter will equal what reading you get from the spring balance upwards. And also from the first condition, you'll find out that the clockwise moments this side should equal the anti-clockwise moments this other side. So that's verifying the conditions for equilibrium. Now, calculations. I'll just speak on these examples. So the first example here, a man of weight 800 newtons stands on a plank. As shown here, the plank is supported by two trestles. Calculate the upward forces at each trestle. So you're going to take moments about this pivot B. So this is going to be your pivot B. So it means you are nullifying the effect of this force here because there's no distance moved from the pivot. Distance moved is zero. So this is your pivot. So we're now considering clockwise and anti-clockwise moments about this pivot. So if you hold here and then look at the weight of the man, it's going down, so it's got a tendency of making this go this way, so that's an anti-clockwise moment. Whereas this force X is going up, and from this pivot here, that's a clockwise moment, so going the other way. So the anti-clockwise moment will be 800 times the 2 meters, which is 1,600 Newton meters here. And then the moment here will be X times the 5 meters, that is from the pivot. So this force times the distance from the pivot, 5 meters, which is going to be 5x. Then equate 5x to 1,600 that you got earlier. So 5x is what, 1,600, and then you find x. X will be the force here. Now, since the downward force is 800 newtons, which means that this force plus this force, upward forces should equal downward forces from the second condition of equilibrium. Like 800 minus this one gives you that one. In the second case here, now you should take into consideration the weight of the plank. Since this is a uniform plank, the weight acts at the center, so it will be at the 2.5 meter mark, since this is 5 meters. So 2.5 meters right there. So you've got to consider the moment of the weight of the meter again, so it is going to be the weight of the meter times this distance from the pivot, which is 2.5, plus this 800 times 2 should equal the clockwise moment, which is 5x again, and then you find the unknown. Be sure to do these questions as an assignment. Signing out.